All right, hello everybody. Just wanted to share some. I'm Victor Lopez. I do not have any conflicts of interest. There's no slide that says that. So just wanted to speak kind of what I've seen over the years of experience I've had. The problem I have seen at different hospitals is that there will be, we're tasked with doing IMRT QA for whatever feedback we're testing, and we use whatever device at that time the hospital has, or whatever. And it seems that the QA program always passes at a different rate. So the question is, well, why does that happen? Is it because my LINAC has become my B model? Is it something with the Phantom? Is it something with setup? And then how good can my QA program be? And essentially through rigorous testing and stuff, we can find out for that site what the baseline is for machine QA for whatever let's say IMRT QA. That's what this talk is about. Some references, SNC Patient Software Guide, TG65, and then assessing the effective electron density in photon calculations. And then a paper I like to think about sometimes whenever I'm doing IMRT QA is MD Anderson paper that was published back in 2014, 13,000 patients on where they QA the patients like 5 times, 3 times with QA devices and then 2 times with film, and kind of how, sometimes it passes, sometimes it doesn't, that kind of thing. And just like a funny thing also that, comes to mind is, let's say you have an IMRT QA that fails. What do? Some physicists will reshoot it and it passes. So now what do? Well, I've seen a lot of times where we just pass. So funny science there. So talking about the SNC arc check with the multi-plug. The reason the multi-plug is because it allows you to put the chamber in the middle there, and I'm sure everybody's familiar with this device. So just some general, so what do? Let's say we go to a site and they say, okay, you got the arc check. And then you're kind of like the physicist is tasked with, okay, how do you set up your QA device to reflect the absorbed dose that you're trying to check, or whatever modulation lead patterns you're trying to check. SNC recommends on page 499, starting there, that, or they say that the density of the PMMA is like 1.18. And then on page 499, they start recommending, hey, actually it's that density, but you need to potentially take into account that it's non-human tissue. And then so we have to go back to TG65, and it turns out that if you take into account that it's not, and the reason it's different, I'm not an expert on this, but my understanding is that it has a different, the Compton range is where primarily we're treating. So in that range, the relative electron density is actually what affects the dose. So for non-human tissue, in this example, PMMA, we just use, I guess, the mean mass attenuation coefficient ratio, and of the 2 different items, you can get it from a NIST XCOM or something like that. And then we get 0.97. And so it turns out that the scaled density as a starting point, 1.15, and that's relative to water, of course. So the next step, now that you know those numbers, you would create a treatment planning system model of your Phantom. For AAA, they recommend AAA PBC XCO chemotherapy. They recommend starting at 1.15 grams per centimeter cube. If you have Eclipse, Monte Carlo, Ray Station, something like that, or Monaco, then start at 1.18. And then it turns out that it's actually field size dependent. Like what's happening with your measurements. And then I'll get into that in just a second. I mentioned that there's a chamber, hole in there for the multi-plug. So they give you the option of, putting the chamber. So now you're checking, I guess, 2.9 cm from the surface for the arc check. In addition, you can check in the center of the arc check with the chamber, which you have TG51 or whatever. And let's see. And then I have listed here the NIST XCOM mean mass attenuation coefficient for water PMMA. And so we can say that don't forget that the dose to a medium is calculated with this. So depending on what you're doing, like for example, if you're overriding the density of PMMA, the entire range, then you're calculating to a medium. But some people will say, okay, well, let me just calculate the chamber as being water. Well, in that case, you don't need to do anything. But just remember what you're doing when you're calculating, because your chamber is calculated for water. So here's some actual measurements. So the starting point was 1.18. So I started with 1.18 or 19 PMMA. And we can see on the right-hand side, so I just compared. So all I did was I compared on the right, the average chamber deviation for different field sizes to the average entry-exit ratio deviation. Oh, so I didn't talk about that. So SMC recommends that you use those densities, right? Either 1.18 relative to water or 1.15. Look at the entrance and exit ratio. And so that's why I'm looking at the chamber in the center and then also the entry exit ratio. So this was a starting point. So, I tried to get, okay, can we get it down to 0.3 and 0.3, something like that? Well, the very next step was, okay, well, let's just see, without overriding anything, what happens when I just use the HU number, no density override, no composition. And the previous slide was actually the composition, because I'm using Accuros, of PMMA. So here is no override. So it doesn't know the composition, it's just HU. You can see that the chamber deviation is like 4.1% deviation positive, and then the entry exit ratio is 8.6. Let me circle back for just a second. So when you do what I have seen is I'll go to a site, check a prostate cancer on 3 and 2, something like that, like 10% threshold, and I'll see like 97% pass rate on a product, just the prostate with the seminal vesicle, something like that. And then maybe we do a lymph node, and then it'll just be like 95% pass rate. And then it would say, okay, maybe that's a one-off, it's highly modulated, or maybe it's because the plant is, highly modulated or something like that. But just consistently through the years, I keep on seeing the same number, whereas at a different site, just using different algorithms, things like that, maybe the pass rate is like 99% on 2 and 1, or 2 and 2, same threshold, 99% pass rate, and it just is constant, hundreds of patients, 99% pass rate, easy. And so that's kind of what prompted me, okay, what happened? Why is this different? Is it the beam model? And in every case, I'm looking at the beam model, the beam model looks appropriate. So there's nothing like strange going on. It's just, for some reason, I'm getting different pass rates. Okay, so sorry, didn't mention that before. So use the HU value. It didn't work out, it was pretty terrible. So then I go to the next thing where I'm just like empirically using the composition of H2O, but I'm changing the density. And then so just going down the rabbit hole here, and just keep on taking measurements, changing densities. calculations, stuff like that, until we get a graph like this. So initially, I thought that, one would think that the chamber can be super low deviation from the treatment planning system, as well as the entry-exit ratio from the treatment planning system. But even with a good beam model, they don't overlap, as you can see here. So the question is, well, when I shoot my IMRT QA, am I shooting it with a chamber? Does a chamber actually matter? Like I never shoot with a chamber. And so for me, the depth that the diodes are at, they use a sun diode of 1, I believe, is more important because I'm constantly measuring that dose, right, relative to the plan. So what I want to do is zero out that entry-exit ratio. And it turns out that for a 6x beam, it's the composition of water and the relative density of 1.18. But if you notice on the right-hand side, circled with a green square, the chamber is actually deviating 2.9%, which is similar to the first slide, which I had the chamber 0.3, but the average entry exit ratio was 3%, something like that. So this is actually the best case. This is what I would recommend. The next step would be, okay, well, what is the dose at that depth? And the SNC recommends, okay, go to like a depth of 2.9 or something like that, and either do it on a flat phantom or a curved phantom, doesn't matter. But what I would recommend is to actually export. So you do your density override, export the plane to your ArcCheck software, and then look at the dose in the ArcCheck software. And then just hover over, the center 2 diodes or center 4 diodes or whatever, on, wherever you're trying to look, and use that number to calibrate your dose. So now what you're doing is like an old school method where we would do chamber and film. We would just normalize our profile to the chamber, whatever it was on that day, because we know, let's say from daily QA, our output is perfect. And so all we're doing is really checking modulation, stuff like that. Okay, so the summary for ArcCheck is 6x, here are the different energies. The entrance-exit ratio on the right-hand side, I got down to zeros, but you can see how the chamber actually deviates, I guess, depending on the beam model, depending on other factors, let's say maybe the electron density, on how it's affected with the energy, each respective energy. So it's a lot more complicated than I initially thought, but so this is what I ended up with as far as numbers. And historically, for more than 10 years, I would just use 1.18, 6 or whatever they recommended PMMA. And so what was happening was at those sites, again, getting like 97% pass rates on prostate cancer, or I'm doing a pancreas and I'm getting barely 95, or if I go down to 2 and 2, it's something else. So the moment that you optimize your ArcCheck, or essentially zero it out to your treatment planning system in this way, now you can see how your program is doing. For example, you could potentially, so what I'm experiencing, maybe I'm jumping ahead. Let me go back to that. For the SRS Phantom, which just is an SRS map check Phantom, and it has PMMA going around it, here's how the field size actually affects the density. And again, I'm trying to choose the right density for the field size that I'm using. And what I mean field size is we know that it's being modulated a lot. Currently, I have a program called ClearCalc. I don't know if people are familiar, but I used to have RadCalc. And in RadCalc, they say alpha all the time, like on the bottom left or something. And so I'm just going off of historical values of what I was seeing on IMRT QAs. And the general thing was an average leaf pair opening through the modulation of about 3 cm. So I essentially zeroed out that, you know, the SRS and the arc check to be at about a 3 cm. So I know that when my field size increases for whatever reason due to tumor, that I will have an absolute dose output different on the arc check software, right? And so that's why if you've ever noticed, you know, that difference, you know, why is this happening? And it has something to do with this. Okay. And then here, this is my last slide. So here's some data. So here's the hardest one is a big breast plan, which we use like easy fluids on. 98% pass rate on 2 and 2. That's it.
Thank you.